In this video, I go over what is meant by impedance reflection. So, in order to see what impedance reflection is all about, we're going to analyze this circuit here where we have a transformer with turns ratio N, and over here on the primary side we have Vs and an impedance Zs, and on the secondary side we have a load impedance ZL. And you can see that the primary values, current and voltage, okay, both RMS, I1 and V1 on the primary side, and then on the secondary side we have V2 and I2. So the first thing we're going to do is define a Z equivalent looking from this perspective here. So this Z equivalent is the Z equivalent of a non-ideal source. Okay, and we're going to denote with the prime just because that's what the book author does. So this Z equivalent does not include the ZS of the source. Okay, it's the Z equivalent to the right of this dashed line. So we can write that this Z equivalent is just the primary voltage, okay, which is the voltage that's to the right of Zs, divided by the current, the primary current I1. Okay, and now remembering the transformation equations that we had from last video, that secondary voltage is equal to turns ratio times primary voltage, and the secondary current is equal to the primary current divided by the turns ratio. Well, we can write this the equivalent of the non-ideal source in terms of secondary values, because V1 is equal to V2 over the turns ratio, and then I1 is just equal to N I2. Now if we just rearrange this, we can show that this Z equivalent of the non-ideal source is equal to 1 over N squared times secondary voltage divided by secondary current. Again, that's a tilde. So if you look up here, well, secondary voltage divided by secondary current, that's just ZL. So you see, this is what impedance reflection is all about, is that when you put a transformer in between two impedances like ZS and ZL, well, now from the perspective of this non-ideal source, you can alter what ZL looks like, okay, or what ZL the transformer sees from the primary side, because this is just equal to ZL divided by the turns ratio of the transformer. And you'll see that this has a very profound impact on matching problems, because this will allow us to match two impedances that we otherwise couldn't match without the transformer. So before we do an example involving this concept, let's go back and recall that maximum power to an impedance load is when ZL is the complex conjugate of ZS. And I just repeated from a previous lecture, what this means. Remember, complex conjugate means, if two things are complex conjugates of each other, or if this impedance is the complex conjugate of this impedance, it means they have the same real parts, okay, so the same resistances, same but opposite sign imaginary parts. So same but opposite sign reactances, which is the imaginary part of impedance. Now, we can write what's called the equivalent circuit for the primary, and this shows what that circuit would look like, where we're replacing, go back to the previous diagram, okay, we're replacing the transformer in ZL, so we're replacing everything to the right of the dashed line where the non-ideal source is with the equivalent impedance, which is the ZL over N squared. So now, if we want to find, if we want to find primary values, if we want to find I1, the primary current, we just have to solve this circuit. If we want to find the primary voltage, well, we just need to find the voltage across here. We can also use this equivalent circuit from the primary's perspective to find, well, what condition do we need for max power when there's a transformer. See, this here that we did earlier in the quarter, this was without transformer, right? Because we didn't even know what a transformer was at that point. So no transformer was involved, okay? But now what we're going to come up with is, what does ZL need to equal for max power to ZL with transformer. Okay, so now this is with the transformer involved. Okay, so to answer that question, we just got to look at this circuit and say, well, the only difference between the case with the transformer and without, as far as the circuit analysis goes, is this 1 over n squared factor, which is just a number. Because remember, n squared is just the ratio of the turns on the secondary to the primary side of the transformer. So we can use the same reasoning that we came up with to find this equality, that maximum transfer to ZL, maximum power transfer to ZL occurs when ZL is a complex conjugate of ZS without a transformer, and just apply that same method to the case with the transformer. The only difference being is that you have this factor of 1 over n squared. So with a transformer, what you're going to end up with is that ZL over n squared has to be the complex conjugate of ZS. See, the only difference between the without transformer case and the transformer case is that 1 over n squared factor that we talked about. So what does that mean? Well, it means when you have a transformer, you want RL to equal n squared RS, and you want the reactance of the load, XL, to equal minus n squared, the reactance of the source. Okay, so this is what you need to get a match, right? Because remember again, that term match means maximum power transfer. So to get maximum power transfer without a transformer, you need these conditions. To get a match, with a transformer, well, now you need to satisfy these conditions. And again, the only difference between the two is the n squared factor that comes from having the transformer in the circuit. Okay, we will finish the quarter with a last video with an example using this concept here of impedance reflection to get a match between two impedances with the transformer that we wouldn't be able to do without the transformer.